Hi and welcome to the webinar. My name is Thijs. I'm the Technical Evangelist at Varnish Software. I'd like to thank you for being here today and taking time out of your schedule. Today I'll tell you a bit more about VCL, which is short for the Varnish Configuration Language. It is in fact the language that powers Varnish and allows you to customize the behavior of the cache to your exact needs. Varnish is an HTTP cache that accelerates websites, but that can also be used to accelerate APIs, OTT video streams, and even allows you to build your very own content delivery networks. As mentioned, I'm the Technical Evangelist at Varnish Software, and Varnish Software is the company behind Varnish. We're the creators of the Varnish Enterprise commercial solution, but also one of the main contributors of the Varnish Cache open source project that powers about 10 million active websites and about 21% of the top 10,000 websites. And in case you're not familiar with how Varnish works, it acts as a reverse caching proxy, a cache that you put in front of your origin web server that pretty much acts on its behalf and offloads traffic. When a client sends a request, it sends it to Varnish. Varnish tries to serve it from cache, and only if it doesn't have it stored in the cache will it connect to the origin server. Let's get back to VCL. VCL is a domain-specific language, meaning that it can only be used with Varnish and has no other implementations. Its syntax has a curly braces style similar to C, Java, and other languages, and it's not a language that you use to program your behavior in a top-down manner. As a matter of fact, there is a standard behavior, a built-in behavior that you can extend through a set of predefined subroutines. These subroutines reflect a finite state machine that has different states and where transactions flow through. And all of this VCL code in the end gets transpiled into C code and compiled when Varnish starts. The main benefits of using VCL is the fact that it's extremely powerful and fast. It's flexible, it has a rich syntax, and where the syntax of the language ends, that's where the rich ecosystem of modules, VMods as we call them, takes over. So what can you do with VCL? What is its purpose? Well, it does request handling, request routing, response manipulation, backend selection, cache control, and also allows you to do decision making on the edge. Speaking of the edge, let's clarify the term. The edge is the outer tier of your web platform, and in this context is represented by Varnish. In smaller scale and more traditional web acceleration setups, the edge and the origin web server, where the content is hosted, can be in the same data center, sometimes even on the same machine. But from a content delivery perspective, where you aim to serve a global audience and reduce network latency, the edge can move a lot closer to the end user. Hence the term delivering content on the edge and making decisions on the edge. It's all about reducing latency. Allow me to introduce you to VCL by showing you a very first snippet. Here it is. It all starts with a version marker, in this case 4.1. Make no mistake, this is in no way related to the version of Varnish itself that you're running. It is the VCL syntax version, which is in this case 4.1, and it can be used with Varnish 6 and more recent. That's why this version marker is there, to avoid incompatibilities of VCL syntax on older versions of Varnish. Then you have a backend definition, which refers to the origin web server. It has a name, in this case default, and has a host and port parameter that point to the network host and the network port on which you can connect to retrieve origin data. Then you have a VCL receive subroutine, which is one of the hooks of the finite state machine you can hook into, one of the states, and where you can perform logic. VCL receive represents the part of the finite state machine where a request is received by Varnish. And in this case, we inspect the request URL using this if statement and try to match the value of the request URL to a regular expression pattern that starts with /admin and then any subsequent subdirectory. If we spot that the URL matches this regular expression pattern, we want to bypass the cache and we perform return pass. But before I can show you many more examples and show you the nitty-gritty of VCL, you need to get accustomed to the syntax. It has a curly braces style, yes, but you need to be accustomed to certain parts of the syntax. Here's an assignment. In this case, we set a value. What kind of value? Well, we're looking at the response object that has an HTTP header called content type, and we're assigning a value to it, which in this case is the content type of the page, which is text HTML with a UTF-8 char set. This is a string assignment. If you set a value, you also need to unset a value, and therefore you have the unset keyword. Besides string assignments, you can also assign different data types. The bresp.ttl variable accepts a duration type, which in this case is an hour, but it could also be a second, a month, a day, a week, or a year. The bresp.status variable and other integer type values expect a numeric value. In this case, that is 503. Here's another one, check this out. And while this is again a very simple string assignment, I wanted to show this example to compare it to long strings. Sometimes your string has multiple lines, and then you use this syntax, where you open up a long string with a curly brace and a double quote, and end it with a double quote and a curly brace. And then all types of characters can be used. You can see that you can open up the long string and close the long string to do variable interpolation. VCL also features if statements. If the expression evaluates to true, you go into the body of the if statement. So in this case, if the request method equals post, then we bypass the cache by performing return pass. You can also do a negation, so a not equal, by using exclamation mark equal sign, just like in any other language. You can have multiple operators there, multiple comparisons, and you can use an and statement or an or statement using a double pipe sign. You can even match against a regular expression by using the tilde operator, as you've seen in one of the first examples. You can also negate that match by putting an exclamation mark in front of your tilde to not match the regular expression. Now, while the action of this snippet does a return pass, these actions don't appear in the wild. They're part of very specific subroutines. So in this case, it fits into the VCL receive subroutine. But there's more subroutines, and they're all part of the so-called finite state machine, which describes the flow of actions within Varnish. Here's a diagram containing the full flow within the finite state machine. It has the different states, which are represented by subroutines, and these represent different parts of the execution flow. And the transitions between the various states happen through return actions, which you can see here. Here's an example of the flow for a cache miss. You start and enter VCL receive. You perform a return hash, which allows you to transition to VCL hash. There you perform a lookup and you conclude that it was a cache miss, which causes a transition to VCL miss. The miss will perform a fetch, which will transition into VCL backend fetch. As soon as the fetch is done, well, VCL backend response will come back and deliver the content. In the end, content that was fetched from the backend is stored in the cache in VCL backend response and delivered to the client. But as mentioned, VCL is not a top-down programming language in which you have to define all the behavior. Most of the behavior is already there, and most of the actions that need to be taken and the transitions within the finite state machine are part of the so-called built-in VCL. The built-in VCL decides when to accept and when not to accept incoming requests, when to bypass the cache or not to store objects in the cache, how to deal with cookies, how to look up objects in the cache, how to deal with stale content, and how long to cache. Here's the built-in VCL code, and let's have a look at VCL receive first, because that's where the transactions start. That's where Varnish receives incoming HTTP requests. The first thing we do in VCL receive is check for invalid content. And if certain content is deemed invalid, a synthetic response is returned. So this is a response that doesn't originate from any backend fetch or anything stored in the cache. In this case, it's a 405 return and a 400 return. This is done through the synth function. The synth function takes two arguments. One is the HTTP status code as an integer, and then the second argument is the reason string that is associated with that. If you don't provide it, like in these examples, the reason that is associated with the conventional status codes is going to be returned. So in the first example, that's 405, method not allowed. The second example is 400, bad request. And this happens, the 405, when the request method equals PRI. That should never happen and only happens when you're receiving HTTP 2 traffic on an HTTP 1.1 endpoint. The second one is if you're using HTTP 1.1, then a host header is required. If there's no host header, we return a bad request status code. The second check will do a return pipe. Piping is connecting to a backend without doing any HTTP anymore. It's just a TCP connection that is opened and the bytes are shuffled through. And this happens when the request method doesn't match this list of get, head, put, post, trace, options, delete, and patch. In that case, we don't recognize the request method and we assume whatever we're receiving is not HTTP, hence the pipe. The last two checks are used to bypass the cache, also for content that is not supposed to be cached. In the first example, we're checking the request method. If it's other than get or head, we're dealing with a request method like post, for example, that will implicitly change the resource, so we can't cache it. In that case, we do a return pass. The second example checks for stateful content. So if an authorization header or a cookie is used, we assume that the content is highly personalized and cannot be served from the cache. Under all other circumstances, we go to return hash, create a caching hash, and look up the object in the cache. If the request received in VCL receive is deemed cacheable, we perform return hash and transition into VCL hash, where we create the hash key. This is done using the request URL and the HTTP host. If you combine those, you have the full URL. If that is the case, then you can look it up. There's also a special case where if there is no host header, you use the server IP. But remember, in HTTP 1.1, you're supposed to have a host header. We've transitioned from VCL receive into VCL hash and returned a lookup, which looks up the object in the cache. And it's good because we found the object that we were looking for, and now we transition into VCL hit. If we find an object in the cache, we need to ensure that it gets delivered and that it's not expired. So if the TTL of the object is greater than 0, we're still dealing with fresh content and we can deliver it. If the TTL is 0 or lower than 0, we're dealing with an expired object. However, there's still some grace time left, represented by the object.grace value. The standard value for object grace is 10 seconds, which means an object can be served up to 10 seconds past its expiration time. However, when that happens, although the content is delivered, the stale content is delivered, a background fetch happens to find the new content. And when both of the cases don't apply, well, then you just return a miss and enter into VCL miss. A lot of the VCL subroutines don't have a lot of exciting things going on. You can see this here. VCL pass, when you bypass the cache, will just do a fetch. The same will happen with VCL miss. When you deliver content, well, it just gets delivered to return deliver. And when you perform a purge, you get a synthetic response saying that the content has been purged with a 200 status code. And then you have these initialization and teardown functions, or subroutines rather. VCL init returns OK, VCL fini also returns OK. So not a lot of exciting things happening. We've reached the point where a backend fetch is supposed to be made. We're in VCL backend fetch. This state is reached when you have a cache miss or a cache pass. Before we fetch, we do another check. We check if the backend request method equals get. If a get request is received, we're actually stripping off the backend request body. It is sent to the backend and it's done through a fetch. And when the backend responds, we end up in the VCL backend response subroutine. Prior to storing the object in the cache and serving it via VCL deliver, we perform a set of other checks to ensure that uncacheable content is not ending up in the cache. If a request was previously marked as uncacheable, then we deliver directly. However, if it wasn't marked as uncacheable, we give it a fair shot at being stored in the cache, but first the next checks need to happen. If the backend response's TTL is less or equal than 0, don't cache it, mark it as uncacheable. This could be if you set an expires header in the past, or if you have a cache control header with a max age of 0 or an smax age of 0. If there's other VCL at play where you explicitly set bresp.ttl to 0, you also end up in this case. If the backend responds with a set cookie header, you're actually changing the state of the response of the resource, meaning this cannot be cached. So again, you end up with an uncacheable object. This also applies if you have a surrogate control header that has a north store value in there, or if there's not a surrogate control header but a cache control header instead that has a value containing either no cache, no store, or private, indicating that the backend doesn't want you to store the object in the cache. And the last condition is if the backend returns a cache variation header, being the vary header, with an asterisk, meaning you want to create a variation of whatever stored in the cache based on every single request value. That shouldn't be the case. It's also perfectly realistic that a backend response did not succeed, and when an error occurs, we skip straight to VCL backend error, which is a subroutine that returns a synthetic response. An error message that didn't really come from the origin, but that was composed by Varnish. And it does so by injecting an HTML template into the bresp.body variable. It does some variable interpolation using context-specific variables and has guru meditation in the output. So whenever you see that, it probably means that you're talking to a Varnish that returned an error message. However, that doesn't mean that Varnish has errors. It just means Varnish couldn't connect to the origin and couldn't get the response it was asking for. There's also a client-side alternative to VCL backend error, and that's VCL sint, which is a subroutine you end up in when you call return sint at the client side. This allows you to generate your own synthetic output without any specific error being triggered, but as a matter of fact, it's already used in VCL receives built-in VCL. Remember that when a request comes in with a pry request method, or there's no host header in an HTTP 1.1 request, then return sint is called with a status code and an optional reason message. Well, that is what ensures that you end up in VCL sint. And the output template is identical. It's the same HTML, similar variables being injected, but just a different context. The thing you need to remember about the built-in VCL is that it gets executed automatically. You don't need to write the code yourself. So the minimal VCL you need is just the version marker and the backend definition. And then the built-in VCL will be executed automatically. However, if your application deviates from the built-in VCL, you need to extend the behavior, you need to write some VCL. So as soon as you start defining subroutines in VCL, you're actually prepending that code to the built-in VCL. Unless, of course, you're performing a return statement, and then you're completely bypassing the built-in VCL for that specific subroutine. One of the first real-life use cases that require writing your own VCL is probably the use of cookies. Nearly every website uses them, and as mentioned earlier, in the built-in VCL, if Varnish sees a request containing a cookie, it will not cache, so it's not really realistic. Here's an example where we filter out the cookies we don't need. It's important to know that there's all kinds of cookies, functional cookies, but also a bunch of tracking cookies. And tracking cookies usually get processed at the client side by the browser in JavaScript. They will only confuse Varnish, so why not strip them off? You can explicitly strip off cookies, but the following VCL snippet actually makes an assumption that only the session ID cookie is required. So what it will do is it'll do a find and replace using a regular expression substitution pattern through the rec sub all function and remove every single cookie that doesn't match session ID. And in the end, if there's nothing left but white space, that means there was no session ID cookie, which means you can strip off the entire cookie header. And because we didn't specify a return action in this VCL snippet, stripping off the cookie will result in the content being cacheable. Leaving the session ID cookie in it means the content is not cacheable, which makes sense because we'll probably need a personalized response using that session ID cookie. Another thing that probably makes a lot of sense is providing the logic to perform cache invalidations. Storing things in the cache is important, but getting them out on a timely fashion is equally important, especially, for example, in the media landscape where breaking news needs to appear on the homepage as soon as it comes out. Well, you can't afford to wait until the content expires. You need to define an active way to purge the cache. And this VCL snippet does that. It doesn't do it unconditionally. We need to define an ACL, an access control list, which contains IP addresses, host names, and subnets that are allowed to perform the purging. And then in VCL receive, you catch the request method and check if it's purge. If it is purge, you'll map the client IP address and see if it matches the purger's ACL. If that is not the case, we return synthetic output. A 405 saying that the client IP address is not allowed to purge. And if the client IP does match the ACL, you just perform a return purge. So in the end, it's all about connecting your CMS, for example, to Varnish and allowing it to do a purge call for a specific URL to invalidate that one from the cache. The next VCL snippet features the use of a vmod. What we do is we import a module called std, the standard module, and what that does is it loads extra functionality into VCL. One of those utility functions is std.querySort, which will alphabetically sort query string arguments for a URL, which makes a lot of sense because Varnish identifies objects in the cache based on the string value of the request URL. If you would shuffle the order of the query string parameters, you would end up with a different string and a cache miss. So to increase your hit rate, std.querySort will just sort the arguments automatically. I covered a couple of examples and they all interface with VCL objects in some way, shape, or form. So it makes sense to go over the various objects and variables that VCL has to offer. One group of variables are the connection variables. These variables are grouped in the client variables, the server variables, the remote variables, and the local variables. In a traditional setup where the client connects directly to Varnish, both the client and the remote IP will be the same, and both the local and the server IP will be the same. But as soon as you start adding proxies and you use the proxy protocol to communicate, Varnish will differentiate. The client will be the original client ID, the server will be the primary server that the client connects to, the remote endpoint is the IP address of that proxy server we are connecting to, and local is our own local IP address. The most common object he used is the request object. It contains all request related information and has a bunch of variables, like the request method, the request URL, the request protocol, and then the rec.http object that contains all the HTTP request headers, such as the host or the user agent or the accept header, whatever it can be. The rec object also has a can gzip property that is either true or false to see whether or not the request can be gzipped. So let's have a look at the example on the right hand side. So we're doing a GET request for the home page over an HTTP 1.1 protocol using the localhost header, and the user agent happens to be curl. The user agent accepts every type of content. So rec.method would be get, rec.url would be slash, rec.http.host would be localhost, rec.http.user-agent would be curl, rec.http.accept would be */*, and rec.can_gzip would be false. When a request cannot be satisfied by the cache, a backend request needs to be made, and that's where the request object gets copied into the backend request object. Most of the properties look the same. There are some exceptions though. So while the method, the URL, the protocol, and the HTTP headers match, there's a connection timeout, a first byte timeout, a between bytes timeout. These timeouts are set to runtime parameters but can be overridden in the backend definition. If a background fetch is made, is bgfetch returns true. And brec.backend refers to the backend object that was selected. If we don't assign a specific backend, the first one that is defined will be used. And the example on the right hand side would yield the same kind of output. So let's have a look at the backend response variables, which are a result of the backend request being satisfied by a backend response. There is bresp.proto to return the protocol, bresp.status, which contains the status code, the reason string is stored in bresp.reason, and all the response headers are stored in bresp.http. You can have bresp.http.content type and .content length if we use the example on the right hand side. bresp.body contains the response body that was returned by the origin server. It's not really a string type that you can read from or write to. It is of the type body, and it can be overridden once, and we typically do that in VCL backend error. But the backend response object has a lot of other properties, like do ESI, which is equal true or false, indicating whether or not the response should be sent to the ESI filter, looking for edge side include tags. Do stream will stream the content through without waiting for it to be buffered completely. Do gzip is to figure out whether or not the content should be gzipped. Do gunzip is a property that says whether or not gzip content should be stored in an unzipped format. TTL contains the time to live that was set through the cache control header, some other piece of VCL or an expires header. It contains the remaining TTL of the object. bresp.age is a response header that is automatically set by Varnish and contains the current age of the object in the cache. bresp.grace contains the remaining grace value, which is the Varnish equivalent of stale while or validate, meaning how many seconds beyond the TTL can stale content be fetched while a background fetch is run. And bresp.keep contains the local keep time, meaning how long past TTL and grace will you keep the object around for. bresp.backend contains the backend, and if we want to mark content as uncacheable, as we've done in the built-in VCL, bresp.uncacheable is set to true. So we already covered the connection variables. We covered the request variables, which get copied into backend request variables when a fetch needs to be made. We've received a response from the body, which allows us to work with bresp variables. Now we're going to store the object in the cache. So as soon as it's stored in the cache, some of the data is available through the OBJ, the object if you will. It has the protocol and the status. and the reason string of the response. Also, all the HTTP headers are available. Every time an object is hit, the object.hits counter gets increased, so that's also accessible. You can access the remaining TTL, the current age, the remaining grace, and the keep value. And if the object was uncacheable, that information is also available in obj.uncacheable. And then again, we can apply this to the example. obj.proto is HTTP/1.1. obj.status is 200. obj.reason is OK. obj.http.content type is text plain. obj.http.content length is 12. obj.hits will be initially 0 but will increase. obj.ttl wasn't really set explicitly in the response, so it goes to the default value, which is 2 minutes. obj.h will start at 0 and will increase, whereas obj.ttl will decrease. obj.grace will be set to 10 seconds, and the keep value, obj.keep, has a default value of 0. And this content seems perfectly cacheable, so obj.uncacheable will be false. Alright, the last step in the data flow involves returning the response from the backend context back via the client context to the user. That makes the response object available, which has similar output as backend response and as object. It has a proto, status, reason, HTTP headers, it has the body, and we also know whether or not it is streaming. And I can apply it again to the example, but you know what's going on probably, right? Before we end, let's use the knowledge we gathered and give you a couple more VCL examples. The first one will override the TTL. We're not doing that for any type of content. We're matching the content type to see if it's an image or a video. And if that is the case, we override the TTL to 1 year to cache it as long as we can, because in essence, this is static content. And here's the final example. We talked about cookies already and the fact that we need to strip off cookies we don't use. What we're doing in this example is actually using the value of a language cookie to create cache variations based on language. So if we spot a cookie in the request header that has a language cookie that matches values like NL, EN, or FR, which are the supported languages, we extract it using reg sub and hash that, meaning that there will be the URL and the host header to identify an object in the cache, but we're adding the language cookie on top of it. So instead of just removing cookies, we're actually using values of cookies to make better cache decisions. That's it, we've reached the end. This is the end of the webinar. Thank you for sticking around so long. I hope you enjoyed yourself and I hope it was insightful. I promise you that there will be more content like this where we will zoom in on individual use cases that require VCL. But for now, you needed to learn the basics. So the things to remember are that VCL is a very powerful language that gets compiled from C into actual machine code, so it doesn't come faster than VCL. It's very flexible. It is a DSL that doesn't require you to write all the behavior. There is built-in VCL that already takes care of most things. The VCL code that is executed in the built-in VCL is structured into different kinds of subroutines, which represent states of our finite state machine. We have a whole range of VMods at your disposal, but even within the confines of the VCL language, there's plenty of objects and variables to use. Thank you for watching. See you next time.